So we got, let's say that you have a graduated cylinder, and I showed you the graduated cylinder yesterday, and we talked about closed-ended air columns. So I've got some air columns here, and if they're filled up with water, let's say this is the same graduated cylinder at 3 different times. I could take my glass cylinder, and I guess I'll do the glass cylinder in red, but I could take my glass cylinder and I can slide it up vertically out of the graduated cylinder. And as I take my glass tube and I slide it vertically out of the graduated cylinder, what's going to happen at different points? If, well, here's the if I take a tuning fork and I ring the tuning fork over top of the graduated cylinder. Yeah.
You're going to get like a resonating point.
Yeah, you should get some resonance, some standing waves that are going to occur, and you're going to hear it as like a louder tone. Okay, and you're going to hear the constructive interference at the resonance points, or the resonance lengths, which is going to sound to you like a louder tone. So the first resonance length, really what's going to be happening inside of the tube is going to be a quarter wavelength. Because since we're not changing the frequency of the tuning fork each time, it's going to be constant hertz. It's the same frequency each time. The wavelength within that tube is going to stay the same. So there's a quarter wavelength. The next one, and yesterday we did a sketch. We said, okay, so a wave looks like this if it's closed at one end. And we said we get resonance when we get to this length. The next resonance that we get to is there, so we have constructive interference at the mouth. The next resonance is there, so we have constructive interference at the mouth. So the next pattern would look like, well, really kind of this fishy-shaped portion of the graph, fish standing on its head. So something like that. And the next length at which you're going to get resonance is going to be at this point. So it's going to be kind of like a loop with an extra fish. So when the waves are like that, constructive interference. Now, if you happen to find that the amount of pipe here that's out of the water, in other words, the length of your air column, is, and I'll just throw out a number. Let's say that we find this to be 0.03 meters, 3 centimeters. Okay? How high should the pipe be at this point out of the water? Why would you say 9? Yeah, it's 3 1/4 would be 3 times 0.3, so that would be 0.09 meters, or 9 centimeters. How high out of the water would you suppose, just prediction-wise? Why would you say 15?
Because there's 4 halves, and then there's another.
Okay, so 4 quarters, quarter, 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 quarter. Yeah, and so we might suppose that this is 15 centimeters, okay, from here to here. Now that's if we measure the first one perfectly. If you don't measure the first one perfectly, that won't be what you found. What's important is the difference between these guys. If I know that this one is 0.9 and this one here is 0.15, that means that at this point here on the graph, 0.9. At here is 0.15, oh, 0.09 I should say, 0.15. From here to here is what fraction of a wavelength? A half, lambda over 2. So for this situation, if I have my measurement at this resonance and the measurement at this resonance, how could I find the value of a half a wavelength? Yeah.
Minus them?
Yeah, 0.15 meters minus 0.09 meters would give me, what's 0.15 minus 0.09? 0.06 meters. So I could say that lambda over 2, or half a wavelength, is 0.06 meters. And if I get lambda by itself, that really means that lambda, 2 times 0.06, is equal to 0.12 meters, or I am producing a 12 centimeter long wave. Fine. Now let's say that I look at my tuning fork, and stamped right into every tuning fork is the frequency at which that tuning fork resonates. So we're going to use some tuning forks. Let's say that we're using one that's 1,000 and I think 1,028. I always get that mixed up. 1,024, 1,028. Anyway, 1,028. Let's say that it's a 1,028 hertz tuning fork. Can I figure out how fast this resonating wave is bouncing back and forth within the column?
Yes.
How do I do it? Sergeant?
Was multiplied by 0.12 meters.
Right. Multiply the frequency by the wavelength. So 0.12 meters, always in meters, not in centimeters, notice, times 1028. Is there anybody with a calculator that could tell me what the speed of this wave is? Yeah, Joseph? 123.36 meters per second. So this wave is really bouncing up and down, echoing within this tube, back and forth, at 123.36 meters per second, if this is what you observed. Now for today, your objective is to get nice observations, to go through the analysis that's in the lab outline, and you're going to do some of this basic analysis, okay? But it's in preparation for something that's happening in the future.